When we are naming alkenes, and this doesn't apply to alkynes, when we're naming alkenes, we do have to pay attention to the shape of the alkene around the carbon-carbon double bond. Different shapes are possible, and the different shapes around the double bonds gives us something that we call cis-trans isomers. Because, you may or may not have learned this in 121, carbon-carbon bonds are not free to rotate. And let me draw a picture of what I mean when I say free to rotate. So let's draw an alkane, not an alkene. We're just going to draw a regular alkane, and we're going to keep it pretty simple. And I am going to draw one chlorine on this alkane. Single bonds, like a carbon-carbon single bond, are free to rotate, which means that this molecule can twist around the carbon-carbon bond. And it's also twisting around all the other bonds as well, but we're just going to think about the carbon-carbon bond. So this carbon-carbon bond can twist and turn. And when it twists, we can see all different types of shapes for the molecule. Like as it twists, maybe the chlorine goes from being in this spot to this spot. And this is something that's freely happening. That carbon-carbon bond is freely rotating all of the time. And because it's freely rotating all of the time, this is why, as we are drawing the structures of alkanes, one of the things that you learned is it doesn't matter how you draw it. You could draw it like this, or you could draw like this, and it doesn't make any difference because this bond is constantly twisting and turning, and the molecule is taking on all different kinds of shapes all the time. Well, that is not the case with carbon-carbon double bonds. So once we get a molecule that has a carbon-carbon double bond in it, that carbon-carbon double bond is locked. The molecule is not going to be able to turn around or twist around at that particular carbon. That's not allowed. So that means that alkenes that have the same atoms but pointing in different directions are two totally different molecules, not the result of twisting. Again, our molecule on the left cannot twist around to form this particular shape. And likewise, this bond cannot twist around to take on this particular shape. It's not an option. These two molecules, these two alkenes that I drew, are just completely different molecules. The molecules are the same in terms of their connectivity. So if we look at how the molecule is arranged, going from left to right, we have a chlorine that's attached to a carbon that also has a hydrogen attached. And then there's a carbon-carbon double bond. And that carbon has a chlorine and a hydrogen. So they have the exact same connectivity, the exact same number of atoms, and the exact same arrangement of atoms. They are only different in terms of the orientation or the shape of atoms with respect to the double bond. If we highlight the double bonds, we can see the molecule on the left has both of the chlorine atoms on the same side of the double bond up top, and the molecule on the right has the chlorine atoms on two different sides. One is up top and one is down below. That's how they're different. The molecule on the left is called the cis isomer of this molecule, and the molecule on the right is called the trans isomer. The cis isomer is the one where the molecule has, in this case, chlorine atoms are on the same side of the double bond. The trans isomer is the one, in this case, where the chlorine atoms are not on the same side. It has one on each side. Cis, in general, means same, where trans means different. Again, referring to the chlorine atoms being on the same side or the chlorine atoms being on the different side, a different side. Cis-trans isomers are two molecules that have the same formula. So looking at our example with the chlorine, these are both C2H2 Cl2. They have the same connectivity. That just means their atoms are connected in the same way. If we're looking at like a condensed structure, which is a really good way to analyze connectivity. A carbon with a hydrogen and a chlorine, and then another carbon with a hydrogen and a chlorine. So these two molecules have the same connectivity. They have a different shape or orientation or arrangement, whatever word you want to use, around a carbon-carbon double bond. Let's look at another example. The molecule 2-butene can exist as cis or trans isomers. Let's practice drawing the structure of 2-butene from its name. So first of all, but tells us that we have 4 carbons. Ene tells us that we have a carbon-carbon double bond, and the 2 is telling us where that carbon-carbon double bond is located. So if we number our carbons, 1, 2, 3, 4, 2 tells us that the double bond starts at carbon number 2 and it goes forward in the carbon chain to carbon number 3. And let's fill our hydrogens in, remembering every carbon likes to have a total of 4 bonds. So we're adding enough hydrogens, adding as many hydrogens as we need to give every carbon 4 bonds. This particular molecule, 2-butene, has 2 possible arrangements around its carbon-carbon double bond. So one possibility, the carbon-carbon double bond, that's carbon number 2 and carbon number 3. One possibility is that the CH3 from carbon number 1 and the CH3 from carbon number 4 are both on the same side of the double bond. So here's our double bond, and we have the methyls, the CH3 and the CH3, both on the same side. Our other possibility is that the methyls, the CH3s, are on different sides of the double bond. So here they are on different sides. When we just look at the name 2-butene, it does not tell us, there's nothing about the name that tells us if we're talking about the cis isomer or the trans isomer. It could be either one. If we want to communicate one particular isomer over the other, then we will use the prefix cis or trans at the front of the whole entire name to indicate the actual shape of the molecule. Now, one thing that's important to notice, we're going to do some more examples of this on a worksheet, but before we get to the worksheet, one thing that's important to notice is that not all alkenes can exist as cis or trans. Not all alkenes can be classified as cis or trans. In order to be classified as cis or trans, you have to be able to find something about the molecule that helps you decide if its substituents or branches are on the same side or on different sides. So let's look at this example. Here's our double bond. And what we're trying to do is determine, is this molecule cis or trans? So one thing that we could do is look at the CH3, the methyl group. And in order to be able to classify this molecule as cis or trans using CH3, we would have to look for a second CH3 and ask ourselves, where is that second CH3? Is it on the same side or is it on different sides? So this molecule only has one, so we can't find a second one to use to help us decide if it's cis or trans, so that's not an option. So now we look at hydrogen, and we've got, let's say we've got this hydrogen right here, and we're going to ask ourselves, what about, is there another hydrogen, and is it cis or trans? And so maybe you could say, oh, you know, here's the second hydrogen right here, so that means they're on different sides, so maybe this molecule is trans. But what if you looked at this hydrogen right here? What about that guy? Well, this guy has a hydrogen on the same side. It also has a hydrogen on a different side. So it's kind of both cis and trans. In a situation like this, you can't call the molecule cis or trans. There isn't a cis or trans. In order to classify as cis or trans, each carbon of the carbon-carbon double bond must have one thing in common. So you have to have one thing on each carbon atom that they have in common. For example, if we're trying to go by a methyl, then the other carbon must also have a methyl in order for us to make that distinction. And also, you can only have 2, not 3 or 4 of any given thing, substituent, or branch, or whatever you want to call it. You cannot have 3 of the same thing. In that case, you're not going to be able to have a clear cis or trans relationship. Let's look at another example where we can't use cis or trans. So first we're going to draw the line of our double bond, and let's just say, let's start with hydrogen. If we wanted to classify this molecule as cis or trans, we have to look for a hydrogen. There must be a hydrogen on the other carbon, and there is not. So we can't use hydrogen to classify as cis or trans. Let's try chlorine. If we're going to try with chlorine, there must be a chlorine over here on this or this side of the molecule in order for us to classify as cis or trans. There isn't, so we can't use chlorine. What about bromine? We only have one bromine. We don't have a bromine over on this side of the molecule. That means we can't use bromine. Let's try CH3. Where's our second CH3? We don't have a second CH3, so we can't use that as well. So this molecule also can't be classified cis or trans. And this one up here also, not cis or trans. Here's one more example, just one last one. In order for us to classify a molecule as cis or trans, each carbon atom can have only one thing in common with the other. You can only have two identical substituents. This molecule has 4 bromines on the carbon-carbon double bond. Because it has 4 of the same thing, we can't call it cis or trans. Let's go to a worksheet and practice this some more.